Okay, let's go ahead and look at another example. Let's look at the limit as x, or let's actually use h. H approaches 0 of 3a plus h quantity squared minus 9a squared over h. Now if you notice, there's two variable sets here. There's a's and h's. Because h is approaching 0, a is a constant then. If a would have been approaching 0, h would have been the constant. But this tells me what my variable is. H is my variable. That must mean a is a constant. So in working with this, I'll plug directly in. And when I plug directly in, I get 3a plus 0 quantity squared minus 9a squared all over 0. So 3a quantity squared is going to be 9a squared minus 9a squared over 0. This is 0 over 0, which is indeterminate. Indeterminate means to do more work. So the more work that we can do, we could try and look at this a couple different ways. Graphically, this is difficult because I have this constant of a I'd have to define, and that would work the same way numerically. I'm not sure how to deal with that. So hopefully some algebraic approach will work here. So let's rewrite our original problem. The limit as h approaches 0. And I'd like to go ahead and expand this. So again, we're going to look at this algebraically. And that's why our algebra skills are so important. And plus it's just fun. So if we expand this 3a plus h quantity squared, I end up with 9a squared plus 6ah plus h squared minus 9a squared. Now the minus 9a squared came from right here. Okay, and this is all over h. Now what's causing me a problem is this h in the denominator. So it's my hope that that h in the denominator will cancel with something in the numerator. Looks like the 9a squareds cancel, and I'm left with h squared plus 6ah. And okay, this looks good. I see that if I factor further, I can factor an h out of the numerator and left with h plus 6a. Now I can cancel my h's. And of course, you were not tempted to cancel the h's here or here because you can only cancel factors, and those are still terms at that stage. So from here we're left with the limit as h approaches 0 of h plus 6a. As h approaches 0, h goes to 0, and I'm left with the limit of 6a as h goes to 0. When you might say, okay, well what do I do because there's no h in here? Well remember, 6 is definitely a constant, a is a constant, so the limit of a constant is a constant. And that is the limit of the function. And you might say, well that doesn't really mean anything. But for now, what we're working with, this is going to be called a difference quotient pretty soon. And it's how we determine the derivative, which is the slope of the tangent line at any point along the graph. And we don't always get a constant. Sometimes we get an algebraic expression. Okay, let's look at another example. In this example, I'm taking the limit as x approaches 1 of x to the 4th minus 1 over x cubed minus 1. Plugging directly in, I get 0 over 0, which is indeterminate. Indeterminate means to do more work. Kind of a reminder there. And we could look at this graphically or numerically, but we're going to look at this using the algebra approach. So again, having good algebra skills is important here. And we're just going to factor the heck out of this thing. X to the 4th minus 1 factors into x squared plus 1, x squared minus 1. X cubed minus 1 factors into x minus 1 over x squared plus x plus 1. Now if you don't remember the x cubed minus 1 factorization, you can certainly use synthetic division or long division to figure that out. You can also type this into Maple and right click on it and ask it to factor. Wolfram Alpha, if you type in x cubed minus 1, will give you the factorization as well. Now as we're working from here, I still don't have anything that will factor. These terms, x minus 1 and x squared minus 1, these factors I should say, look very close to being able to cancel, but not quite. I have a squared term there. So I need to keep working. Limit as x approaches 1. X squared plus 1 does not factor any further. The sum of perfect squares does not factor nicely. The difference of perfect squares does, however, and that leaves me with my x plus 1, x minus 1. And this takes care of my problem, because the problem was the denominator was equal to 0. And what made it equal to 0 was I was subtracting 1 minus 1 right here. And that, my friends, is about to cancel. And because those cancel, I should be able to get a reasonable limit here. Limit as x approaches 1 of x squared plus 1, x plus 1, and in my denominator x squared plus x plus 1. And we should be able to take the limit now. Let's go ahead and plug in that 1. 1 squared plus 1 times the quantity 1 plus 1 divided by 1 squared plus 1 plus 1. So it looks like I have 2 times 2 over 3, or 4/3 is my limit. And of course you can check that in Maple. You can look at it graphically as well. So that's another example. Let's go ahead and end this particular section with a very fun algebra problem. Now remember, very little of this is calculus. We've hardly done any calculus at all. It's all been algebra. Let's go ahead and take the limit as x approaches 4 of the square root of 5 minus x minus 1 over 2 minus root x. Of course, we plug directly in. 5 minus 4 is 1. Square root of 1 is 1. 1 minus 1 will be 0 here. 2 minus the square root of 4 would be 2 minus 2, which is 0. This is indeterminate. And of course, indeterminate means to do more work. Well, ideas. Well, let's look at algebra here. Let's look at rewriting this and simplifying it. Of course, multiplying by the conjugate always seems to be a good start to one of these. So let's multiply by the conjugate. Now, the question is the conjugate of what? Because I have two choices. I have the conjugate of the numerator and the conjugate of the denominator. And the answer is, try one and see what happens. So I'm going to go with the conjugate of the denominator. And again, I'm just going to try this and see what happens. This might not work, and it may work. So let's go ahead and multiply it out. I'm left with the limit as x approaches 4. I'll look at the denominator first because that numerator looks a little bit ugly. So if we look at that denominator, I end up with a nice 4 minus x. The numerator, I'm going to FOIL this out. Remember, first outside, inside's last. First outside, inside's last. From way back when. And I'm going to get 2 root 5 minus x for my first. My outsides are going to be plus root x, root 5 minus x. Insides minus 2, last minus x. Nothing combines. I could get some things to factor, but it will factor right where we started at. So I really don't get anything to cancel here. This almost looks worse. If I plug 4 directly in, I get 0 over 0 again, which is indeterminate. And of course, indeterminate means to do more work. But we just got done doing more work. So we must have chosen the wrong conjugate. So let's go ahead and start over on this one. And sometimes that's going to happen. Sometimes you're going to try something and it's not going to work, so you have to start over again. So let's look at the limit as x approaches 4. And again, of our original problem. So I have my original problem then, and the original problem was square root of 5 minus x. And again, you have to be careful what's underneath that radical sign. 2 minus root x. Now last time we multiplied by the conjugate of the denominator. This time let's go ahead and multiply by the conjugate of the numerator. And after you work a lot of these problems, you'll start to see some trends of things that will work and not work. So, maybe in a while we realize that, getting rid of that binomial underneath the radical really works pretty nice. So we're left with the limit as x approaches 4. It's kind of a bad line. And what I don't want to do is I don't want to FOIL out this denominator because you can only cancel factors, so we want to leave it in factored form. So I have 2 minus root x, square root of 5 minus x underneath the radical sign plus 1. And again, I don't want to FOIL this out because if I FOIL it out, things get more complicated because I want to be able to cancel the factors, and so I have to leave it in factored form. Now the numerator I can FOIL out. I'm left with 5 minus x minus 1. So I have the limit as x approaches 4. 5 minus 1 is 4 minus x for my numerator. 2 minus root x. Root 5 minus x plus 1. So here we have the limit as x approaches 4. Now how does 4 minus x factor? It factors into 2 plus root x, 2 minus square root of x. 2 minus square root of x, of course, we're dragging along into the denominator, root 5 minus x plus 1. Now again, we hope something will cancel here. The 2 minus root x's cancel. And I'm left with the limit as x approaches 4 of 2 plus the square root of x over root 5 minus x plus 1. So plugging directly in, we get 2 plus the square root of 4 over root 5 minus 4 plus 1. So I have 2 plus 2 over 1 plus 1. 2 plus 2 is 4, 1 plus 1 is 2, and I have 4 halves, which is 2 here. So 2 is my limit. Now these problems are fun. Lots of algebra involved, very little calculus, and that's one reason why your algebra skills need to be very, very strong. That's probably about it for the techniques that we have for evaluating limits for a while. We will look at some other limits eventually when we get into looking at horizontal asymptotes, and in Calc 2 when we learn L'Hopital's rule. But now we're going to be jumping into some trig limits, okay, and then also we're going to be looking at the intermediate value theorem as well this week. Thank you.